All right, guys, I sent out a poll, and sorry, we only had not a very high percentage that wanted to actually jump on a video at 7:45. So here we are. I will be available. Just email me. We can do a Google Meet if you have any questions. But here is what we're doing today, right here. So that's the homework. I'm going to just go over a couple of vocab items and then the logic of a significance test, sometimes called a hypothesis test. All right, so if you have the packet, turn to page 2 and just read this top. So I claim I'm an 80% free throw shooter, and then to prove my skills, I did a sample for you, right? So this is what I'm claiming my P is, 0.8, the true proportion of free throws that I'll make. And then I have a sample. Sample size is 50, as you can see, and I only made 32. 32 divided by 50 is 0.64. Okay, so here's the first sign of, something up is 64% is quite a bit less than 80. Okay, so real quick example. I got this email just this week, and it made me think of what we're learning today, so I wanted to show it to you guys. So, just right here, this teacher said, my son services the forklifts at Built Bar. It's just it's a protein granola bar built. They're pretty good, actually. They say they taste like candy bars. It's a pretty bold statement that I don't really agree with, but as far as protein bars go, they're not bad. Anyways, they have bars that they gave him that are underweight or overweight. Now, if you think about it, this company's losing money just giving these away, but they can't sell them because they're not meeting the specifications. So they have this sample, right? They have all the bars that they've ever made. What proportion are underweight and overweight? Right? Is that devastating to their business? Are the machines broken, or is it just part of normal variability? So they could benefit from what we're going to talk about today to try to figure out, is this happening by chance, or is it an actual issue that they need to look at, right? So back to me. Yeah, not everyone's going to hit 80% free throws every time. If you've watched your favorite team or gone to Westlake basketball, people miss free throws when they should make them. Okay, that's normal variability. But is this too low to be part of normal variability? That's what a hypothesis test will help us with. Okay, so my population is all the free throws shot. I'm saying that I hit 80%. My sample's 50. I only hit 32. Okay, so like I showed you with Built Bar email, like here, do we have evidence that something's going wrong? Yes, Built Bar has evidence because they have these bars that are underweight, overweight. Their machines are supposed to make these specific weights. So what's going on, right? And we have evidence here. This P hat is evidence that I'm not really 80%. Now we know not every sample is supposed to hit the true proportion, but how much variability is really okay? All right, so number 3, basically 2 possible explanations. Man, it's just a rough day for Miss Buse. We're going to call this the null hypothesis. It's just a rough day. Her true P is really 80. She's just having a rough to go, right? She's distracted. I don't know. Something going on. Okay. Number 2, well, maybe she's lying about that true proportion. Okay. Alternatively, I don't think she can get 64% if she's an 80% just by variability or just by a rough day. I think something's up, and I think her P is really less than 0.8. That's the alternative. Okay. Now, there's other explanations, of course, but this is what we focus on in a hypothesis test. Okay, number 4. Does a statistic, though, give convincing evidence? Nope. Because some things go into samples, sample size variability, or we just have some evidence, not convincing evidence yet, okay? So the logic of a hypothesis test is that we will test our statistic to a sampling distribution and see, could that sample happen by chance? Could that sample occur by chance alone, right? Or is something up? That's the basic logic, right? We're going to see, all right, with normal variability, is this just happening? Okay? All right, and we'll always test it to the sampling distribution for the null hypothesis, right? We'll always innocent until proven guilty, give them the benefit of the doubt kind of situation. Okay, so our null, like I said, our null hypothesis is where you assume the original P is correct. That's always your null hypothesis. Okay, our alternative hypothesis can change. You can just say, hey, I don't think she's an 80% free throw shooter. You don't have to specify. The problem will usually specify. Or if my statistic would have been better, you could have said, well, I think this is better than that, right? Then I give you an A. Just kidding. All right. So these alternative hypotheses, if you use these symbols, they're one-sided. If you use this symbol, it's a two-sided. We'll get into that a little bit more. Okay. Your p-value is going to be the percentage of times we could get p hat or higher given the null is true purely by chance. So we're going to look at our sampling distribution, right? So there's tons of p hats here. Okay. Pretend there's lots. Okay. And I'm supposed to hit 0.8. I didn't. I hit 0.64. So our p-value will be, well, what's the probability that she gets 64 or lower? Yeah, there's a 50% chance she could have got that just because of sampling variability. Don't call her a liar. Something like that, okay? So that's our p-value, the percentage or probability that it happens by chance. Okay? So statistically significant, something's going on, not by chance. And this has to do with our significance level. So this basically gives us a boundary of how to know if something's happening by chance or not. So medical professions usually use a 1% significance level. So if it has less than a 1% chance of happening, then they'll say it's statistically significant. We'll tend to use the 5% to know if we should reject the null. Okay. So that's kind of what's going on. Is we'll go over that. So, all right. So we've actually already done a significance test before. We did it on the very first day. If you remember when we talked about joy and Parkinson's disease, and you didn't test it to a sampling distribution because you didn't know about those yet, but you tested it to a simulation. And in our simulation, there was 0% chance that Joy could have guessed, if you remember that. And so we said, yeah, Joy can smell Parkinson's. Well, we have convincing evidence that she probably can because she could not have done this by chance. There was 0% chance according to our simulation. So remember, if you look back at your notes and look back, you actually have done this before. We didn't use the correct vocab, but we started out with a significance test, the year. All right, so we're actually going to do it. So I write the hypotheses. The null is, yes, Ms. Buse is still an 80% free throw shooter. Variability, bad day, just happened, okay? Alternatively, though, we're like, nuh-uh. It can't be that low just to be a bad day or just to be variability, okay? All right, so we have to check conditions since we're going to use a sampling distribution to compare it. So we make sure that it's a random sample. Yeah, Miss Peace just went out and shot a random group of 50. It's independent because her knowledge of between each trial. Now this is, if you're a psychologist, you might say it's not really independent, but it's more muscle memory usually for free throws. So if I make the first, it has no, it doesn't change the probability of making the second. Okay, and large counts, I made 32, which is greater than or equal to 10, and I missed 18, which is also greater than or equal to 10. So if you look at your formula sheet, you'll see these formulas, but this is the sampling mean, right? The mean of all the samples will hit 80, and we assume innocent until proven guilty, so we assume the null is true when we're testing. All right, so 80% is going to be the true mean there, the true mean proportion, which is the mean of the sampling distribution. And the standard deviation means each sample will typically be about 0.06% from, so about 6% from the mean, right? So if you notice, I use the p, we're back to having p. So in the sampling distribution, I have p times 1 minus p over n, because we get to assume the null is true, so we get to use that normal p, whereas with confidence intervals, we had to use a p hat. Here we get to use the normal p. All right, so you can see I labeled this 0.8, and then I used 0.06 to go out 3 standard deviation. So it's already not looking good for me, right? 64% is pretty far away, all right? And so what I did here to find this actual value, right, is I want to know what percentage of the samples are going to fall at 64% or lower. This is a one-sided test, right, because of my alternative hypothesis. Just a reminder, this is a one-sided test. I'm only looking at one side. Okay, so what, in all these samples that could have happened in the sampling distribution that we're able to recreate, what's the probability that I got 64 or lower? Well, you could use table A, you could find the z-score. So we could find our z-score, the value minus, sorry, I did that backwards. Value minus mean divided by the standard deviation will give us the z-score, or that's not correct. So that, if I put that in my calculator, I'll get that. Or I can use the calculator. So I hit stat, I go to norm, not stat. Yeah. No, sorry. All these things on the calculator now. I hit second, vars, then I go to norm CDF. All right, and on lower, I put a really low negative number. And then on upper, I put 0.64. And then on the mean, I put 0.8. And standard deviation, I put 0.06. 0.06. And I hit enter. And then when I rounded, so this is my p-value. My p-value is the probability that this happened by chance. This sample could have just happened randomly, right? And there was a 0.004 chance that was the proportion of getting a 64 or lower. So at a 4%, sorry, not 4%. I got a 0.04% chance that this is happening. Gosh, I'm struggling with my numbers, right? I got a 0.4% chance of this occurring just randomly, which is less than our boundary. Remember our significance level boundary. Where do we write that? I don't know. Next page. Yeah, our significance level boundary of 5%. Where'd we go? Yikes. Here we are. It's definitely less than. So this is the conclusion that we'll make. And you'll see this as you look up the answers to the problems that you do. Assuming the p-value, no. Sorry. Assuming the true proportion is 80%, the probability of getting a sample. Now, once I put the hat on the p, I know it's a sample. So the probability of getting a p-hat of 0.64 purely by chance is 0.004. We reject the null. Miss Buse, you're not an 80% free throw shooter. We have convincing evidence now that you're not. All right, so guys, that's a hypothesis test. Look over the notes. Let me know if you, as you do the homework, look over the answers. Let me know if you have any questions. I'll be available all day. Just shoot out an email.